So welcome to this video on System Design 101. So in this video, we'll scale a system from 0 user to 100 million user. And through this, we will add new elements that can help in performance, latency, and you learn about these elements and how system design works. So let's get on to it. So this is a basic architecture of, let's say, a photo service. So user can upload a photo and download the photo. So when on the left hand side, you have clients, which is browser, where being accessed from laptop, and second is the mobile app. Now a user will type, let's say, photoservice.com on the browser, and then browser queries the DNS to get the IP address. Then IP address is where it will make the API hit, in this case a GET request. And once the GET request hits the web server, which has the business logic encoded, it gets the response. Now, from the language standpoint, the web server is generally coded in Java, Python, and other, while the client here, for the case of browser, would be JavaScript, HTML, CSS, while the mobile app would be something like Java-based application. So this is a simple architecture. Now, let's dive deeper into what is the API, the basics of API here. So these are the three basic aspects of the API. The first one is to know is API endpoint. So whenever you make the request, this is the address where you hit. Your request is of a different type. You could make a GET request, which is to get the data, put request to upload certain data. There is update and other kind. So in this case, a user make a GET request to get the user data, and the response here is a JSON format. Now this JSON format, or it could be XML, another, your client-side logic, which is the JavaScript or HTML, understand how to render this and present it in a form which is visual and easy on the eyes for a customer to understand. Now let's add a new element to this. So one aspect is that from different session, you might need certain data points that, let's say I query now, but I need all of my details that I have put up in the past, maybe I also need to know about 10 of my friends. So all of this persistent data kind of things is stored in a database, which makes it really easy to store data, query data. So we've added this database to the architecture. So now any response, let's say I want to get my 10 friends who I can share this photo with. So I make a request. The request goes to the database server, and the database server responds with the data, which web server then encapsulates in a way that the client logic would understand. The web server and database communication is generally SQL. So web server will query write a SQL query and fetch the data, which data will be then encapsulated in the form that the client understands. Now, let's say this is 1 user, 10 user, or let's say 100 user. Now, let's say your website become hit and you start getting 1,000 users who are hitting the server simultaneously. Then this server will not be able to handle. So now we have two options here. The first option is that we scale the server, which is called vertical scaling, highlighted here in the left. So you keep scaling the server size so that it can handle more requests, process it. There are some downsides to this. It's costly to scale to buy these beefier equipments. And second is still there is a one point of failure. What if this goes down? Also after a point, you will not get a larger, beefier machine. So general scaling way in most cases after a point becomes horizontal scaling, where you get cheap commodity server and keep adding more, where even if few server goes down, you will hit other server. The challenge here is that now your application logic has to be distributed. It has to understand that it's querying different server. It has to understand the failover logic and other, which makes programming a bit complex. But this is a general way in which application now scales, and this is called horizontal scaling. Now, one way to handle this horizontal scaling is to put a load balancer in between. So what I'll do in this case is when the client is querying, the DNS will give the IP address of the load balancer, and now the load balancer has this logic that which server to hit. If there is a lot of traffic on the server 1, it will hit server 2. If 2 servers are down, it knows that it has to hit server 3. So this load balancer makes it easy. There are a lot of algorithms on how you can optimize load balancer, either round robin or how to understand hotspot and other. For example, one server might have certain data about celebrity, which might get a lot of it. So how to handle that is one of the interesting problems. Now let's take the next layer. So your server is now scaled, but you are querying the same database. So you might your database will be hotspotted and will have performance regression. So one way to scale database is to have primary and secondary architecture, where the primary database is where you write the data, which is replicated to these secondary databases. Now, in order to read or serve to the application logic, you could also serve from the secondary. So let's say your one of the secondary database is down, then you can still serve from the other secondary database. And let's say your primary database is down, then your secondary database will be promoted to primary. There are also other architecture, which is active, and other, where even if the primary is down, you can serve from the secondary, another primary's database. Now, another way to improve the performance of the database is to put a cache in between. So cache is a very high performance storage, generally in memory. So let's say you have the data of leaderboard data, for example. So leaderboard data is very frequently assessed. Maybe it's your top visited page. So in that case, you can cache this data. So the first time server makes a request for this leaderboard data, it hits the database. Now it queries and gets that data. But from the second time it hits, it's served from the cache and is very fast. Now, there are different algorithms on how this cache storage has to be managed, because cache storage is expensive, generally limited. So there are restricted policies around eviction. So let's say you put eviction policy on data which was not used in last 10 minutes, or maybe you have put it on, certain business logic and according to which you want to evict the data. So there are interesting logic you could study about how to manage the cache. Now, there are different storage options for different optimizations. For example, if I have a lot of unstructured data, which are okay to be served at higher latency, then object storage is really easy, it's cheap. If I want to get serve unstructured data at lower latency, then block and file are a good option. In the case of structured data, you have either relational or non-relational store. In the case of relational, MySQL, RDS, Cloud SQL are pretty good way of serving the data. In other cases, if you want to serve data really fast in memory, then Redis and other are good caches. There are also key value store like DynamoDB, Redis, which are really useful for certain kind of operation. There is also vector databases. For example, if I want to do analytics and other where I want to find nearest neighbor, then this is pretty helpful. So these are some database and storage option that you could also use for different kind of workload. One other thing to optimize serving is a CDN. So CDN are sort of servers located in a very in distributed manner. So let's say I'm querying something from India, then there will be CDN server from Mumbai that will serve me the data. So this, so let's say you have to get image about you. Then instead, first time what happens that's when you query, the CDN will go to the origin, which is the original server, and get the data and serve you. But from the next time onward, this data is cached in the CDN and served from the cache. CDN is pretty powerful technology, like Netflix and other use CDN pretty heavily. Akamai is one of the example of CDN, Fastly, and others. So that's now let's include all of this in our original architecture. So now in this case, any static data is served by the CDN to the client. This static data in turn gets the data from the object storage. So all of your videos will be stored in this object storage. Your certain dashboard and other, which are hits really frequently, will be served from this cache so that the performance is high. And then your database is also now replicated so that there is redundancy and also faster serving. There are a few more architecture elements that I wanted to highlight. So the one architecture element which is called messaging queue. This helps in asynchronous communication. So the producer here could be an application that produces a message which will be then written to this queue, and this queue holds this message for some time based on the policy that is written, and then your consumer asynchronously can read the message from the queue. Now this is pretty useful because the producer and the consumer don't have to read and write at the same time, and you can scale both of these also independently. So one of the example in our architecture could be, so let's say I want to do analytics on which customer is uploading how much data, which of my server is getting hit. So I can pass all of these server elements, events to a messaging queue. And this messaging queue will do two things. One, it will write to something like object storage where it will be stored permanently. And second, it will also dump the data to something like Hadoop, Snowflake, and other data warehouse engine, from where I can do data analytics and build a business dashboard. So now this is your complete application where a customer is served using load balancer, hits a server, and that server for hot data queries to the cache. For cold sort of business logic hits the database. Your static content is served by CDN, and the stale content has to be got sort of new content will go from object storage to CDN. And the business user can do analytics using Hadoop or Snowflake and other, where this data is dumped using messaging queue. So in this video, we covered how you can start from a simple architecture, add certain design elements and pattern to scale to serve millions of users. Now, the design pattern we highlighted here can be used in most system design questions. So just to recap, here are the top 5 things. First is build redundancy in every tier. So for example, for server tier, we added different servers, then added a load balancer. In the case of databases, we added secondary databases, added replication. You could also study the concept of sharding, which is pretty useful. One tip here is that generally go for horizontal scaling unless you have strong reason to go for vertical scaling. The second is for frequently accessed data, use cache is pretty helpful. For the case we highlighted, like leaderboard, where that page is accessed really frequently, you could cache the data there in a cache store like Redis. Tip number 3, for static content, if you want to serve them at lower latency, and also for a distributed audience that is global, use CDN. They are pretty powerful. The websites like Disney's, Netflix, and other use them heavily for serving video content. Tip number 4, use a messaging queue. It's pretty important architectural element when you want to scale producer and consumer separately or want to build an event-driven architecture. And tip number 5 is to use microservices. So for example, in our case, for doing the analytics, we put up a messaging queue and built a separate system of storing the data in Snowflake or other data warehouse, and then querying it for business user. Similarly, let's say you wanted to build an architecture where you wanted to do real-time or a batch transcribe of the data, or do detection of images in the photo. So in that case, you could build a separate microservice which does this function and serve users separately. So these are the 5 elements that are pretty helpful. Try using that in your next system design question. So that's it for this video. See you in the next one.